Right. So, hello everyone. This is the second lesson on microcontroller and digital electronics. So, in this second lesson, we will discuss about filters. So, filters is something which removes unwanted material. For example, you have water filter, which cleans the water for drinking. Similarly, in cars, you have three types of filters. You have air filter, which gives clean air to the engine. Then you have fuel filter, which cleans your fuel. And then you have oil filter, which cleans the engine oil. So all these filters, they remove unwanted material, the material which we don't want. Quite similar in electronics, these filter circuit, they are used to remove unwanted noise or unwanted signal, right? So it's quite important in electronics. These filter circuits, they are very important, right? So today we'll be looking at the analog filters as well as digital filters. So analog filters, they use components like capacitor, resistors, inductors, and op-amp, right? Um, we'll look at digital filters maybe later in this module. Now, these are the things we are going to study today. So, for filters, this website. So, if you click on this all about circuits, it will take you to a website. And that's quite interesting, quite a detailed website. Okay. It's quite a useful resource. You can read more about filters from this website. Now, the electronic filters, they remove frequency component in a signal that we don't want. So basically, they remove noise. For example, we might want to remove noise from audio signal like music signals, or speech signal in a phone. Also, the power lines which carry electrical power, they also need filters to remove unwanted signals. So we would like to remove everything that we don't want, but it's not that straightforward. So at most, what we can do is we can reduce unwanted signal. Right? We can't remove altogether the noise and the unwanted frequencies. The maximum we can do is reduce. Right? Um, Sometimes we can also enhance wanted signal, the signal which we want, make them stronger using filters. But we will not be discussing about that in this module. Right? Uh, we'll look at some of the passive filters, which uses passive components, something like your resistor, capacitor, and inductor, which do not produce energy of their own. So those type of components, they are called as passive filters. Right? which basically consumes energy. So resistor, capacitor, and inductor, right? They are your passive component. So we'll study about analog filters using passive components, or we call them passive filters. And we will also discuss about active filters. So these active components, they, for example, your op-amp is a active component, right? Which amplifies your signal, output signal, right? So we will study both these types of filters, active filters and passive filters. Now you may already know about noise. So an analog and digital signal, they both can have noise. So here in this analog signal, we have a low frequency signal and some high frequency noise. Similarly, the digital signal also have high frequency noise. Right? So that's the part we want to remove using filters. So we would like to remove these unwanted signal in a communication system like telephone network, electrical power network, and maybe from a music signal, right? So we have something called as triple N harmonics. You can read about them using this link to protect components such as motors, um, speech and audio processing, then image processing, and then music production. So these are the different applications of filters where we use filters. Right? We can use them to protect some electronic components, for example, motors, uh, processing speech signal, image processing, and music production. And obviously, we use them in communication systems. Now, here we have the different types of filters. Let's start with the left hand side signal. So, this is your original signal, right? And it's a complex signal. It has low frequency components, middle frequency components, and high frequency component, right? Now the amplitude is getting smaller with frequency. So for higher frequency, you have higher amplitude. For medium frequency, you have slightly smaller amplitude. And for low frequency, you have the lowest or smallest amplitude. Now, the low pass filter will only allow low frequencies to pass. Okay. The high pass filter, it will only allow the high frequency signals. Now, the low pass filter, they will remove the middle frequency and the low frequency. And the high pass filter, they will remove the low frequency and the middle frequencies. Right? They remove all the other frequencies, and only in case of low pass, it will allow only low frequencies, right? And it will remove all the other frequencies. In high pass, it will allow only the high frequencies, pass, and remove all the other frequencies. Right? Now, this band pass filter will only allow frequencies in the middle range, right? These ones. And it will remove any frequencies above that, any frequency higher than this range of frequency, and any frequency lower than that. Okay. So basically, as the name suggests, band pass will only allow a band of frequency. Okay. It will allow only a range of frequencies to pass. Any frequency above that, it will remove. Any frequency lower than that, it will remove. Right? So it will only allow a band of frequency, a range of frequency. The opposite is the case for notch filter. As you can see from this response, it will reject a range of frequency. Okay, so as you can see here, it's rejecting or removing a band or a range of frequency. It will allow any signal with a frequency higher and lower than this range. Okay, so it's kind of just the opposite of band pass filter. Okay, so these are the four main types of filter. Now from CNI module last semester, I hope you all remember the Bode plot, the magnitude and the phase plot, right? So we had the amplitude in decibel dB on the vertical axis, and along the horizontal axis or along the x-axis we had the frequency in logarithmic scale. Right? So we are going to use a lot of Bode plot to show the working of these filters. So a low pass filter, it will allow low frequencies to pass, all with same amplitude. So if we look at this Bode plot for this low pass filter, so along the x-axis you have the frequency, and along the y-axis you have the signal in dB, in decibel. So a low pass filter, it will allow all the low frequencies with same amplitude. You can see. Okay. So these are the different frequencies which it is allowing low frequencies to pass, and they have the same amplitude. Okay. Or same gain. Right? And the higher frequencies, they will have lower gain. Right? So some of the higher frequencies, they will be passed but with lower gain. Okay. High and same gain, I would say. All the low frequency signals, they are passing with a higher and same value of gain. But for high frequency signals, you have lower gain in case of low pass filter. Quite similar in case of high pass filter, or basically it's the opposite. It's giving a high and same gain for higher frequencies, right? All these are higher frequencies. So it's giving a high gain and the same value of gain, right? It's constant. But for lower frequencies, this high pass filter, it's giving a lower gain. Right? Now, in case of band pass, it blocks both the lower and higher frequency, and it allows only a certain band uh, in the middle to pass. In the figure, we have a narrow band filter, but we can also have much wider band. Okay, so you can have maybe something like this, a wider band. Then your notch filter. So it's the opposite of band pass filter. So it blocks a specific frequency, a specific range of frequency. For example, in electrical power system, if we are working at 50 hertz and we want to get rid of harmonics or noise at 100 hertz, 150 hertz, so we can use this notch filter to block those harmonics at other frequencies. So it's all the same, which I've already explained. You can read about them. Now here is a Bode plot of low pass filter. So at low frequencies, we get the same gain, A0. Okay. So it's also called as the low frequency gain. So A0 is also called as the low frequency gain in case of low pass filter. Okay. Now, in a filter, we would like to block all the frequencies above a certain frequency. However, in real filters, instead of a sharp drop in gain, right? Ideally, we would like this type of a response, but real responses are slightly, they don't drop all of a sudden. So in a low pass filter, we allow all the frequencies to pass until the gain drops by 3 dB. Right? So from this low frequency gain, this is your minus 3 dB. So this is the point up to where the low pass filter will allow all the frequencies. Right? So although you want your filter to cut off at this frequency, but your actual cut off frequency will be this FC. Okay. And until this frequencies, it will allow all the frequencies to pass. So as we can see, we get some additional frequencies in the output. Cutoff frequency, I've already explained. Then roll off. So roll off is basically the slope, which is in dB per octave. So it's this slope. So the slope is also called as roll off. Okay, and it's calculated in dB, decibels per octave, or dB per decade. So just a reminder, octave is twice the frequency. So if you are starting from 1 kilohertz, one octave is up to 2 kilohertz, twice, double. And decade is 10 times. So if you start from 2 kilohertz, your decade is all the way up to 20 kilohertz. Okay. Right. So first, we are going to study about passive filters, which consist of passive components like resistor, capacitor, and inductors. So as I've said, these passive components, they do not produce energy. They are passive, sleeping, right? They don't consume, they only consume energy. They don't produce energy. Whereas active filters, they consist of components like operational amplifier, or in short, we call them as op-amp, right? So these op-amps, they sometimes amplify the signal also, right? So they add energy to the system. Now, in this slide, you can see some of the advantages and disadvantages of a passive filter. Okay, I'm not going to go through all of that. You can read it after the class. Just have a RC, or a filter consisting of resistance and capacitance only. Okay, this is the simplest passive filter. So I have this circuit on multi-sim, and we can have a look at this. So you can see this is your circuit. It consists of a resistor of 1 kilo ohm and a capacitor of 19.9 nanofarads. Okay. Now this is your signal generator. So it's generating a waveform, a sinusoidal waveform of 1 hertz frequency and 10 volt as the peak voltage amplitude. Okay, so maybe we can right. So this is quite a simple circuit. You can implement it on your own, or I'll be using a couple of circuits in today's class. So if you go on Brightspace, section 2, filters. In section 2, I have uploaded all the circuit diagrams or multisim circuits for all the circuits. Right. So this one is your passive filter, which we are discussing. So you can download them and try them out yourself. Okay, so if we run this, we are getting this type of a response, right? So as you can see, it's allowing all the lower frequencies, right, with the same gain. and it is, um, all the higher frequencies, they are at a lower gain. So cutoff frequency, you can easily calculate, uh, and the formula is 1 over 2 pi multiplied by the value of resistance and capacitance. Okay, so that's the cutoff frequency. So in lower frequency range, we can see the gain is almost constant and it's 0 dB, right? So the cutoff frequency is, um, 3 dB. Up to 3 dB, we allow the frequencies to pass. So the cutoff frequency would be, since this is 0, will go down to minus 3. I'm looking at this number. Okay, so we'll go down to minus 3, would be somewhere here, right? So that's minus 3 dB, and the frequency is 7.99 or 8 kilohertz approximately. So that's my cutoff frequency for this filter. Okay. Now, slope. So we just now discussed about slope or roll off. Okay. So we need to find that also. So let's, for slope, let's take, maybe, let's take a little higher value. Let's take maybe 40. So that's about 40. So minus 14 dB approximately, I would say. And 1 octave will be double of that, so 80. So let's check the amplitude or the gain at 80 kilohertz. So if we drag it, so it's minus 14, and then if we drag it to 80, so about like 20 dB. So from minus 14 to minus 20. So that's a slope of around minus 6 dB per octave. Or if you want to calculate the slope in decibel, dB per decibels. So we started from 40 and the value gain was minus 14. So a decade will be 400. So you'll have to go all the way up to 400. 409. So that's approximately 400, 409. So we are getting around like minus 34 dB. Minus 34 dB at around 400. So from minus 14 to minus 34, it's around minus 20 dB per decade. Okay, so that's how we calculate the slope and the cutoff frequency from the graph. Okay, now let's try and change the value of resistance. So currently it's 1 kilohertz. Now let's change it to make it double. Let's make it 2 kilohertz and see what's the effect. So you'll have to stop it and run it again. So let's see. minus 3 dB. So this again, the gain is 0 dB approximately in for the lower frequencies, and my cutoff frequency will be minus 3 dB. So that's about minus 3, and we are getting around 4 kilohertz, right? To get so for 1 kilohertz, my cutoff frequency was, let me check it again. So for 1 kilohertz, my cutoff frequency was around 8 kilohertz. And if we double the resistance, the cutoff frequency reduced by half. So from 8 kilohertz, it was changed or reduced to 2 kilohertz. Sorry, 2 kilohertz, 4 kilohertz. Right. Now, so this is about your low pass filter. Now, to get a high pass filter, what we can do is we can just swap or switch the resistance, the position of resistance and capacitance. Okay, so the output currently we are measuring across the capacitor. Now, if we change it and connect it across the resistor like that, we will get a high pass filter. Okay, so if you swap the positions of resistance and capacitor, you'll get a high pass filter. So this is your high pass filter. You can calculate the cutoff frequency and the slope yourself. Let's quickly maybe check the cutoff frequency. So for higher range of frequencies, again 0 and minus 3 dB is approximately here. So around like maybe 4 kilohertz. It would be, yeah. So around 4 kilohertz is the cutoff frequency for this high pass filter. But since this is your high pass filter, now we call them as upper cutoff frequency. Okay. For low pass filter, we call them as lower cutoff frequency. And for high pass filter, we call it as upper cutoff frequency. You can calculate the slope yourself. Okay. So if we come back to our slides now. So we just saw a low pass filter with a single RC, resistance and capacitance. So if you have a single resistance and capacitance, that's called as a single pole filter. Okay. And we measured the slope of that filter. So it was around minus 20 dB per decade or minus 6 dB per octave. Right? So for a single pole RC low pass filter, the slope is minus 20 dB. Now you can combine two RC filters together, something like this, and that's called as your two-pole filter, RC filter. What it will do is it will uh, increase the slope. So if you have a two-pole RC filter, the slope will be minus 40. Then similarly, you can have a three-pole, four-pole filter like that, and they will have a sharper slope, a very sharp slope, which we usually require. We don't want some of the additional frequencies passing through the filter. We want a sharp cutoff or a sharp slope. Right? So we can achieve that using higher poles or higher pole filters. But there is a catch, there is a limitation, or there is a problem. So when you are adding these RC components, resistance and component, you can keep on adding them, but as a result, it will lead to a less efficient circuit. So all these passive components, they will consume energy, and ultimately you will get a very inefficient circuit, right? Although you will get a sharper slope or a higher slope, but your circuit will be less efficient, and you will get a very big filter circuit. You'll have to connect so many components. So you'll get a very big, bulky circuit, and that will be inefficient. Right? So it's not that straightforward. Now, this is the formula for calculating critical frequency or cutoff frequency, FC. Right? Sometimes it's again, you have multiple names. You call it critical frequency or cut off frequency, FC. So FC is 1 over 2 pi RC. The value of resistance multiplied by the value of capacitance. Okay. Now this is a typical exam question. So you can get something, a numerical, something similar to this. So you have a passive RC low pass filter, which is made of 180 ohm resistor and 2 microfarad capacitor. So you have to sketch the circuit diagram, calculate the critical frequency, and draw the Bode plot for the output. Okay. So this is the multi-sim circuit. So I've used multi-sim online. Even you as a student can also use multi-sim online. Okay. I will quickly show you the link. So again, if you go on your Brightspace and go to module introduction, just yesterday I added the link for multisim online. So if you click on this link, it will take you to this website, the official website of multisim. Although I'm logged in, but you will have to create a login, a profile using your UHI email, and then you can create your circuits on multisim. Okay, so you can, if you don't have the installed version, you can use multisim online. Okay, so this circuit I have drawn using multisim online. You can also use it. Now, to calculate the cutoff frequency, it's very simple and straightforward. So my resistance, it was 180 ohms, and the capacitor was 2 microfarads. So just be careful, you'll have to do the conversion. So if you have to multiply it with 10 to the power minus 6. If you calculate that, I'm getting 442 hertz. Okay. And again, you can plot the Bode diagram on multisim. Okay. So passive filter, they have a low frequency gain of around 0 dB. The minus 3 dB will be somewhere here. So that's your minus 3 dB, and the corresponding frequency is 442, which is your cutoff frequency. And we can calculate the slope also, right? Slope of this portion. Now, basically, the reactance XC of the circuit, it changes with frequency. When you have different frequencies or a range of frequencies, this resistance is unaffected. There is no effect of frequency on resistance. But this one, the capacitor, it will be affected by the frequency. Okay, so it changes the reactance of the circuit. Right? So your capacitance will change, but your resistance, it will not change. So that's why we'll have different reactance at different frequencies. So at low frequencies, the value of Xc will be very large. Right? For smaller frequency, Xc will be very large. So the current will be small. Right? So the current flowing through this resistor, it will be very small. And the voltage across this resistor will be also small, according to Ohm's law. Right? And we end up getting a large voltage across the capacitor. You might remember the Kirchhoff voltage law. Like you might have studied KVL, Kirchhoff voltage law. So this is your supply, and you have a small voltage here, right? So all the remaining voltage, because in a loop, voltage is the sum of voltage drop should be equal to your supply voltage. As a result, you will have a very large voltage drop across this capacitor. Okay. So for low frequency, you will have large voltage across the capacitor. And we are measuring the output across this capacitor. So obviously the output voltage will be large. Okay. And over here, the voltage drop across the resistor will be very small, almost equal to 0. So your output voltage will be equal to V in, or it will be very close to the input voltage. Okay. At high frequencies, the XC, the reactance, it becomes small. So the current flowing through the resistor, it will be large. It will increase. So you will have large voltage drop. Again, according to Ohm's law, if you have large value of current flowing through this resistor, V equals to IR. So you will have a large voltage drop across here. And as a result, the voltage drop across the capacitor will be small. Right? So for higher frequencies, you will get lower output voltage. Okay, that's how your uh, low pass filter works. Don't need to worry too much about all these formulas here. Um, Now, um, the high pass filter, we have already discussed this. So in the high pass filter, we have just swapped or reversed the position of resistance and capacitor. And now we are measuring the output across the resistor. Okay. So this is the response of a single pole high pass filter. The band width is from cutoff frequency to the maximum frequency. So that's your bandwidth. Starting from your cutoff all the way to the maximum frequency. Okay. Now, along with the capacitor, we can use inductor to build a filter circuit or to design a filter circuit. So inductors, they also have inductive reactance. So in case of capacitor, we had capacitive reactance Xc. Inductors also have reactance, which would change, which will be affected by the frequency. Right? So we can use LC filter also. Inductors, they are opposite of capacitor. So in case of inductor, a low frequency can pass easily and high frequency current does not pass easily in inductor. Right? So we can use inductor, but they are not perfect because they have some internal resistance which is susceptible to um, electromagnetic interference, right? And they have poor tolerance. So this is how we can implement filters using inductor. So at low frequency, we will have high current passing through the inductor. So at low frequency, we'll have high current passing through this inductor because inductor, they allow uh, lower frequencies to pass easily, right? Which may not pass through this capacitor. So capacitor and inductor, they are opposite of each other. Inductor, they allow lower frequencies to pass easily, but capacitor doesn't, right? So this current may not pass through this capacitor, but it has an alternate path. So it can flow through this output resistance. So low frequencies will pass through this resistor quite easily. Now, at high frequencies, we will have low current passing through the inductor. Okay, so now if you have high frequencies, you will have low current passing through this inductor. The current itself is very low, so it doesn't really matter if the current is flowing through the capacitor or the resistor. Ultimately, your output will be low or smaller for higher frequencies. Right? So using this design, we can develop a low pass filter. Okay. And then this diagram is for high pass filter. So as you can see, we have swapped the position of the inductor and capacitor. We have changed or reversed the position. Right? So at high frequency, this capacitor will allow large current, right? And this inductor may not allow those higher frequencies to pass. So we have this alternate path. All the large current will flow through this resistor. So ultimately you will get a high or a larger output, right? And again, at low frequencies, this capacitor, it does not support low frequency signal, or so your current will be lower. And again, it doesn't matter if it flows through the inductor or the resistor. Ultimately, your output will be low because your current is low. Okay. And the cutoff frequencies, the formula for cutoff frequency is here. It's quite similar to the previous formula. So for RC circuit, we had 1 over 2 pi multiplied by RC. But here we have an additional square root, right? So now the formula for LC circuit or LC filter, it becomes 1 over 2 pi square root of inductor multiplied by the value of capacitor, LC. Okay. Now let's look at this circuit on multi-sim. LC high pass filter. So your capacitor, it's of 100 microfarad, and the inductor, it's of 100 millihenry. So you can use the formula which we have discussed. So 1 over 2 pi square root of inductor L multiplied by C. Okay. And if you do the calculation, you should end up getting somewhere around 50 hertz. So I've done the calculation. It comes out to be 50.33 hertz. So that is the cutoff frequency. Now let's have a look at the Bode plot. So this Bode plotter, you have so many different display here. You have your function generator, oscilloscope on the right hand side, right? So you have the Bode plot somewhere here as well. You can use it. Now, if we run the circuit, for that we'll have to stop this one and then run this circuit. So if we run this circuit, we get this type of a response. Okay. Now we are getting a peak here. So this peak is at the cutoff. So if we, maybe I can, I want to increase the size of this so that it's easier for you to see. So that's the peak, and it's around 49.9, approximately 50 hertz. So we are getting a peak at our cutoff frequency, right? And it's giving us a gain of about 28 or approximately like 29, 30 dB approximately. We are getting a gain of 30 dB here. So it's mainly because of resonance, right? So this happens because of resonance. Now, although in the cutoff frequency, the formula, we don't have the resistance. We only consider L and C. We don't have this resistance. But let's try and change the value of resistance to see what is the effect on the output. So from 1000 ohms or 1 kilo ohm, I've changed it to 100 ohms. Okay, I have to stop it, and then if we run this again, so as you can see, when we reduce the value of resistance, the peak, it reduced. And again, if we change it to maybe 10 ohms, so yeah, at 10 ohms, the peak, it disappears. But obviously the cutoff frequency is no longer at 50 hertz. So that's about 0 dB, right? That's about 0 dB. And if we go back to minus 3 dB, so at around 3 dB, you can see the frequency is 145, 146 hertz. So it's no longer at 50 hertz. So R1, the resistance R1, although it is not included in the formula for cutoff frequency, but it plays a critical role, right? So again, it shows like it's always not straightforward. Things are not always straightforward, right? So coming back to our slide, um, right? So that peak we were getting. So resonance, they occur around the cutoff frequency of the filter, which can lead to a peak in the output. Before roll off or before the slope starts, we get a small peak at our cutoff. Now, quality factor or Q factor. Um, it's the resistance. Basically, they act as damping. So quality factor is affected by the value of resistance which we are choosing. So it kind of act like a damping component in the circuit, right? Similar to CNI, if you remember. Okay. Now, we will study about some of the active filters. Since passive filter does not provide any gain, they simply allow a lower or a higher frequency to pass through. So we need an active filter with an op-amp, which along with filtering the signal, it will also provide us gain, some little amplification it will give. Okay. So in an active filter, we have an op-amp and a RC circuit at the input. And this RC circuit or your input, it is connected to the non-inverting terminal. Right? Then you have a feedback connected to the inverting terminal. Okay. So this is basically a non-inverting amplifier. This configuration, if you remember, it is your non-inverting amplifier. And the formula for voltage gain is 1 plus the RF divided by R1. So that should give us the frequency gain, right? If it is a low pass filter. Then based on the value of R and C, that will decide what range of frequencies can pass through, right? So RC circuit, at the input, they will filter the signal, the input signal. And this op-amp, it will provide amplification. Okay, so this is your basic structure of an active filter. Now, this is your first order RC active filter. Right? So here you at the input, you have the RC filter and you have the op-amp. Okay. Let's look at this figure or this circuit on multisync. So all right, so this is your RC active filter. So here you have your resistance and capacitor, and this is your 741. I'm using the most common operational amplifier, 741. And this is your RF and R1. Right? So the low frequency gain, it will be 1 over RF divided by R1. So that will be 4. So 1 plus 3 divided by 1, it will be 4. And if you convert it into decibel, that is, take log of that and multiply it with 20. So log of that will be around 12 dB. Okay, so we should get 12 dB gain. Okay, in the so this is connected as a low pass filter. So we are taking the output across the capacitor, right? So this is a low pass. So we should get a gain of around 12 dB in at lower frequencies. So if we run the circuit, we get this type of response. So let's check. So in the low frequency, as you can see, we are getting 12.04 dB. With RC passive filter, we were getting 0 dB, around 0 dB. But for an active filter with the current components or the values, we are getting 12 dB, quite close to what we have calculated. Now the cutoff, so from 12, if you go down minus 3, that will be 9 dB. That's about, let's go down to 9 dB. And yeah, so 8.9 or 9 approximately. So we are getting, let me try and just, yeah, that's more accurate. So around 9 dB or at 9 dB, we are getting 483 hertz. So that's my cutoff frequency. Now for this RC, if you calculate the value of cutoff or the cutoff frequency, if you calculate, so it's 1 over 2 pi multiplied by RC. So if we do 2 pi multiplied by resistance is 3300 multiplied by capacitor is 100 nanofarads. So that's multiplied by 10 to the power minus 9. And if we take inverse of that, so we are getting about 482 hertz by calculation. Right? So this RC is giving us a calculated cutoff frequency of 482 hertz. And here we are getting 483, close enough. Okay, and the slope. So you can again calculate the slope. So let's start at maybe a little further. So at let's take it here around 10 kilohertz. So at 10 kilohertz, we are getting minus 14.41 or 14 dB, minus 14 dB approximately. So 1 octave will be 20, double of that. So that's around 20, and we are getting around 20 kilohertz approximately, 19.09 or 20. So that's, so from minus 14 to minus 20, that's around minus 6 dB per octave, right? And if we go down to maybe 100, it's around 34, 35. So from minus 14 to minus 34, that's about 20 dB per decade slope, right? So for a single pole or for a single RC, we are getting the same minus 20 dB per decade or minus 6 dB per octave. The slope for single pole filter will always be minus 20 dB per decade or minus 6 dB per hour. That's what we are getting here. Okay. So that's your RC passive filter. Okay. Now, so this is again a typical exam style question. So you can again be asked to calculate the cutoff frequencies, sketch the diagram, and the gain. You can be asked to calculate the low frequency gain in case of active filter, right? Sketch the Bode plot and the output. So basically we are given with a single pole active low pass filter, which is made up of resistance of 160 ohm, capacitance of 200 nanofarads. Okay, and R1 is given as 10 kilo ohms. Okay, so first we have to calculate the cutoff frequency. Okay, so cutoff frequency, the formula is 1 over 2 pi multiplied by R and C. Okay, so resistance is 160 ohms, capacitance is 200 nanofarad. So you have to convert it. And we are getting 490, 49, or like 4.9 or 5 kilohertz. Okay. And this is the circuit from Multisim Online. And we can calculate the roll off, right? And basically, as we know, for this is a single pole filter, you are having only single pair of R and C. So for single pole first order filters, the slope should be about minus 6 dB per octave or minus 20 dB per decade. Okay. And this is the Bode plot for from Multisim. Now again, we can verify the value. We can calculate the roll off from the Bode plot, right? You can select a value and then go down go down double that frequency to get your slope or roll off in dB per octave, or you can go down 10 times. If if your first frequency was 1 kilohertz, you go down 10 kilohertz. That will give you your slope or roll off in dB per decade. Okay. You can go through that numerical, maybe a little more in detail on your own. Right. So we have looked at passive filter using RC and RLC circuit. Then we have looked at the first order active filter using op-amp. Now, our ideal filter should have a very sharp cutoff. That is, it should have a steep slope after the cutoff frequency. Ideally, it should be vertical, right? But for first order system, we are getting a slope of minus 20 dB per decade or minus 6 dB per hour. So we can increase the slope by using a second order filter. That is, instead of a single RC, we can use two RC filters, right? To increase the slope to minus 40 dB per decade. And then we can increase it further by using a third order filter. So for a third order filter, the slope will then increase from minus 40 to another minus 20. That's altogether minus 60 dB per decade. Right? If you use a third order filter. However, with increase in the order of filter, we can although have much sharper cutoff, but it will lead to other disadvantages, like making your circuit more complex and um, ripples, right? Which we will look at in the next slide. So for higher order filters, ripples is quite a concern, right? So there are different types of active filter and we can choose the best one. So here is a electronic tutorial second order filter. So this is again a link to a web page with more details about the second order filters. If you are interested, you can go through it. So these are all the second order filters. So there are like different types of filter. You have Butterworth, Bessel, Chebyshev, and elliptic filters. Okay, so Bessel. So as you can see, this is the response for a Bessel filter. So it's quite smooth in the pass band, but you have the slope. The slope is not very sharp, right? It has a larger value of. It has a smaller slope, right? Although in the pass band it's quite smooth, but the slope is quite large. In case of Butterworth, again the slope is again the response in the pass band is very smooth, but again the slope is not very sharp, is it? In case of Chebyshev, you can see the slope is sharper, but in the pass band you get ripples. Same goes for elliptic. So again in the pass band you have ripples, but the slope is much more sharper. Okay, so the message here is you have to balance between the good and bad for these filters. So maybe in some application, your requirement is to have a sharper slope. You don't care much about ripples, or you can do with some ripples in the pass band, but you need a sharp cutoff. So in that case, you can use either Chebyshev or elliptic. But if in your application you need a very smooth uh, uh, response in the passband, and you can deal, or it's okay for you to have a slope, slightly larger slope, then you can choose either of those, like Bessel or Butterworth, for smoother passband response. Right? So you have to choose between these based on your application. Uh, no need to memorize this. It's just an illustration that we have different types of uh, second order filters, or more than two pole filters. So one of the thing about, or one of the limitation about a second order filter is that we get a resonance peak, right? So you get a peak at your cutoff frequency, which we don't want, but we might have to accept it. Now, the size of the peak will depend on the quality factor, or the damping factor, dF, or this Greek letter zeta. Now, dF is given by this formula here, 2 minus Rf divided by R1. So these are your feedback resistances. Right? And the damping factor, it cannot exceed 1. So this dF, it cannot exceed, it cannot be more than 1. It will always be some decimal value. It will be 1 when Rf and R1, they are equal. Okay. Now for example, the damping factor that we require to achieve a Butterworth response for a two-pole filter or a second order filter is 1.414, and this will correspond, so 1.41 is around, is it's like square root of 2, and the corresponding resistance ratio, that is Rf over R1, is 0.586. So we can use that to calculate the low frequency gain. Okay, so the low frequency gain, it comes out to be around 4 dB. Now this is a Sallen-Key second order filter. It's similar to our first order or single pole filter, active filter, but along with your RC, you have additional pair of resistance and capacitor. Right? So basically, you have two resistances and two capacitances connected at input. But they are at different position. So this capacitor, it is used as in the feedback to the non-inverting terminal. Right? So I have this circuit on multisim. So let's have a look at that. Okay, so let's go to multisim, and let's look at the next one. So this is your So this is your high pass filter. Sallen-Key. Let's have a look at this Sallen-Key filter. Just let me. Right. So let's look at this Sallen-Key filter. Now you have two pairs of so you have two pairs of resistance and capacitances, right? So one of them, like 68 nanofarads, it's being used as a feedback here. Okay. And RF is 100 ohms and R1 is 180 ohms. So the low frequency gain from the formula which we have seen is 1 plus RF over R1. So this will be 100, 1 plus 100 divided by 180. So that gives us 1.55 or 1.56. And if we convert it into log, so 20 multiplied by log of 1.56. If we do that, we get around 3.86 dB. So that is the gain in the low frequency or for the low frequency. Okay, so in the low frequency, this is the response, and in low frequency, the gain is around 3.8. You can see, right? And we get a peak here. So this is either we like it or not, we'll always get it for higher filter circuits, right? Now this is a second order filter. So the slope should be double of the first order. That is, it should be around 40 dB per decade or 12 dB per octave. So let's check the slope. Okay, so let's check the slope here. Let's choose a frequency, start frequency, maybe a little further down. Let's choose 6. That's around 5.9 or 6 kilohertz, and the gain is minus 12, around minus 12. So if we go one octave, so double of that, so double of that frequency will be 12 kilohertz. Okay. From 6 to 12, if we go down, that's around 12. So the gain is minus 25. So from minus 12 to minus 24, minus 25, that's around 12 dB per octave, right? So for a second order filter, we get twice the slope twice the slope of a single pole filter. Now, just one more thing. If we change the value of RF, maybe if we increase it to 180, so that my RF and R1, they are equal. So in that case, my gain will be uh, 1 plus 180 divided by 180, that's 2. And if you convert it into decibel, it will come out to be 6 dB. 20 log of 2 is 6 dB. So if you run the circuit, the gain, obviously the if you increase the value of RF, the peak will reduce, and you should get around 6 dB. So that's around 6 dB, which we are getting. Okay. So you might get a lower gain, but your peak, it will reduce. Okay. So if you want to get rid of that peak, you can use a higher value of RF, but your gain will be lower. If you want larger gain, then you will get a peak. Okay. Now coming back to the slide. So these are the formulas. So again, the low frequency gain is 1 plus RF over R1, and the cutoff frequency, if you want, you can calculate the cutoff frequency for the multi-sim circuit, which we have just now seen. Okay. It's 1 over 2 pi RC, a square root of, previously for single pole it was RC, but for two pole filter circuit or a second order filter circuit, it's 1 over 2 pi square root of RA, RB, CA, CB, all the resistance and capacitances multiplied together. Now, if your resistance, if the two resistances, they are same, the capacitances, they are same, then you end up getting the same formula as for a single pole, 1 over 2 pi RC. Okay. Now, here is an example. So you are given with a second order Sallen key, low pass filter. Resistance, the two value of resistance they are given, the capacitances they are given, the value of RF and R1 is given. So you have to calculate the cutoff frequency, Bode plot. You have to sketch the Bode plot, calculate the damping factor, and again the output on multisim. So using the formula, it's quite simple and straightforward. Just be careful with unit conversions, right? So most of the time, capacitance and inductance, they will be either given in millihenry or microfarads or nanofarads. So you have to know the conversions. Right? So if you convert it, we are getting 2.2 kilohertz. And this is a two pole filter. So the roll off or the slope will be minus 40 dB per decay. Now, the gain, low frequency gain, RF over R1 plus 1. So this is the number. We are getting 2.6. And if you convert it into decibel, you'll get 8.52. And the damping factor, DF, is 2 minus Rf over R1. So again, quite simple formulas and quite simple calculations um, for the filters, but you have to be a little careful when you are using the values or to implement the formulas correctly. Okay, so DF, damping factor, is about 0.67. This is again from Multisim, the output response, Multisim online or Multisim live. Now, next thing is multi-stage filter. So we can have different response or slope or roll off by having higher order filters. Okay, so just now we saw for second order Sallen-Key filter, the slope we can change it to -40, or we can have a higher roll off or slope. Okay, but we can also do that by cascading or connecting single pole filters, right? So we can connect in series maybe 3 filters to get a third order filter or get a slope of -60 dB. Or we can connect 2 filters, 2 single pole or first order filters together and get a slope of -40 dB. Okay. Now, you can do that, but the overall gain will be, if it is in numbers, if your gain, individual gains, they are in numbers, the overall gain will be multiplication of the individual gains. G1 multiplied by G2 multiplied by G3. But if your gain is in decibels, dB, then the overall gain will be sum of the individual gain. Okay. So you have to be careful, right? If the gains are given in decibel, you have to add them. But if they are given as a number, maybe 6, right? Then you have to multiply them. 6 multiplied by 6 multiplied by 6. Whatever value you get. But if it is like 10 dB, so it will be 10 plus 10 plus 10. Right? So can quickly maybe show you the circuit. Maybe this one. So this is quite simple. As you can recognize, this is one filter and this is the other filter, which are cascaded together. Simply, you connect the output of your first filter to the next filter. And the value of resistance and the capacitances, they are also the same. RF, R1, everything is the same. Just two same filters which are connected together, back to back or in series. Okay, so maybe we can first check the output of a first order or a single filter over here. Okay, so using this R and C, we can calculate the cutoff frequency. So it will be 1 over 2 pi multiplied by R0. So if I do the calculation real quick, 2 pi multiplied by 3300 multiplied by 1 microfarad. 10 to the power 6. And take inverse of that. So we are getting around 48.2 hertz, right? So let's quickly verify that. I have to stop this one and then run this. And so again, gain will be 1 plus 1 RF over R1. So it will be 2, right? And if you convert it into log, it should be 6 dB gain, right? We have done the calculation for one of the circuits. So gain, low pass gain is 6 dB, and from 6 to minus 3, that is 3 dB. So if we go down 3 dB, that's around 3 dB, and the frequency is coming out to be 49, 48. We are getting 48. Here it is around 49. So quite close to what we expected. Okay. So that's for a single pole or a first order filter. Okay. Now let's check if we connect two first order filter or single pole filters together, what will be the slope? Okay. So let's check the output now. So we are getting a gain of 12 dB. So 12 minus 3 is 9. So 9 will be my cutoff frequency. So cutoff frequency, it's coming out to be around 29, right? Near about half. We were getting around 48 for one for first order filter, and if you have connected two of those, it's around 29. Okay, and the slope, let's take maybe 100, maybe 200. Yeah, so 13 dB, and double of that will be 400. So minus 24. So that's a slope of 12, around 12 dB per octave. Okay. So that's your simple, like two first order filters which are connected together in series or cascaded together. Right. Now coming back to the slide, don't have much now, should be able to complete in time. So here we have an example. So we have an active filter consisting of 3 stages cascaded together. The first stage has a gain of 3 and 2 pole. The second stage has a gain of 5 and 1 pole. And third stage has a gain of 1.5 and 3 pole. What is the overall gain? So since they are given in numbers, so the overall gain will be multiplication. They are not in decibels, right? So 3 multiplied by 5 multiplied by 1.5, right? And then you can convert it into decibel. Okay, so you get a gain of 27 dB approximately. And if you add up all the poles, so you get like 6. Okay. So your overall slope will be for one uh, pole, for a single pole, the slope is minus 6 dB per octave or minus 20 dB per decade. So for 6 poles, your overall slope will be either minus 36 dB per octave or 20 multiplied by 6, it is minus 120 dB per decade. Okay, so it's a simple, short numerical, maybe asked in like short answer question. Now, the last one is your band pass filter. Okay, so maybe we can have a look at directly the multi-sim circuit. Okay, so let's stop this one. So band pass is also quite similar to your two-stage filter. Okay, it's if you look at the circuit, it's quite similar. The only difference is, if you see it carefully, here you are taking it is RC, right? You are taking the output from here and connecting it to op-amp. You are measuring the voltage across capacitor. So this is kind of a low pass filter. Okay, but on the second stage, you have a high pass filter. We have swapped the positions. Okay, capacitor is there and then you have resistor. So you are kind of taking the output across the resistor and connecting it to the second op-amp. So let's quickly run this circuit. RF, R1, they are the same. And so that's your band pass filter. So it will allow a range of frequency, a specific range of frequency, and reject any frequency higher or above those frequencies and lower than that frequency. Okay, so this is your response. And for band pass filter, you have a center frequency. Okay, let's come back to our slide. Maybe you can try this circuit on multisim on your own. So that was the right. So because it is a band pass filter, we have a center frequency FC, which is used in the formula for quality factor. Although maybe for you don't need to remember these formulas for the exams. So in band pass filter, we need the frequency where we get the maximum gain, and that is your central frequency. We also need the bandwidth, which is the difference between the upper and the lower frequencies, right? And the quality factor um, is given by this formula. So a low quality factor means wider bandwidth, and a high quality factor means narrow bandwidth. Okay. So this is all that we wanted to discuss in today's class. And these are the tutorial questions and the MCQs.